All right, this is question 7. Explain why, according to kinetic theory, a gas exerts a pressure on the walls of its container. You will need to use the idea of momentum as well as that of pressure. So yeah, they've very kindly given us some hints here. Kinetic theory, then, remember, is just the idea that we can explain the pressure exerted by gases in terms of just the motion of the particles and the collisions of the particles. So 3 marks for this question. There's going to be 3 points to be made here. I would kind of open by just saying the particles in the gas move with random motion. That may not be one of the points, but it's a kind of, it's a precept, if you like. It's kind of pretty fundamental to kinetic theory. So I'm going to open with that. I'm not sure if it's actually in the mark scheme as one of my 3. So that's my opening gambit. What happens then to exert a pressure? Well, the important bit here, and I'm sure this would be one of the 3 points I need to make, the particles collide with the walls. Those are elastic collisions, remember? And therefore they rebound. Therefore, the particles experience a change in momentum. Oops, that's not quite how you spell momentum. So those particles are going to collide with the wall. They rebound in the opposite direction. They must have experienced a change in momentum. No change in speed, but remember, momentum is a vector. And I would just put some reference to the idea that force is equal to change in momentum over time. Particles experience a change in momentum, hence force exerted on them. And then I'd mention Newton's third law. Which says that, you know, if there's a force exerted on the particles, there must be an equal and opposite force on the wall. And then, because it does say as well as that of pressure, so we need to link that force to pressure. If you think about the wall of a container, it will experience many particle collisions over its area. And pressure is equal to force over area. And that's job done. I may have gone into slightly more detail than is necessary. I think quite often in this type of question, you know, there will be 3 points. There's 3 points available, and you could just make 3 points and absolutely get those if you're sure what's going to be on the mark scheme. Frequently, the mark scheme will have more than 3 points and will say any 3 from. So it may be that we've overkilled this ever so slightly, but. Yeah. Part B. At one instant, 3 molecules in a sample of gas have speeds in meters per second of 394, 453 and 527. Calculate the RMS speed. So this really is just a test of, do we know what RMS speed is? And hopefully we do. It is the square root, the root of the mean of the squares. So that's RMS stands for root mean square. It's the square root of the mean of the squares. So that's going to be equal to the square root of, and I just need to then square each of them and take the mean. So 394 squared plus 453 squared plus 527 squared. All of that is going to be divided by 3. There's 3 of them. I'll chuck that in the calculator now and we'll get an answer. .461.2. meters per second. You've always got to be a little bit careful with RMS because normally the context in which we use the RMS speed, it's being squared, and often students forget that you do need to then square the RMS value. They kind of, because the name is slightly confusing, it's called the RMS, it's called the root mean square. That value itself is not squared. When you use it for kinetic energy or something like that, you would then have to square that root mean square. So really, in the kinetic energy formula, you're using the root mean square squared. Or if you prefer, just the mean of the squares. Okay, speed of sound in nitrogen at 3 temperatures is given below. There is a simple mathematical relationship between Vs and CRMS. Okay. Determine this relationship showing your reasoning. Okay. So 4 marks for this, which is quite a lot. We have 3 temperatures, 100, 200, 300. We've got 3 velocities for, speeds for sound. So what we would very much like is some link between the RMS speed and the temperature. And luckily such exists. If we were to look in the formula book, we would find PV equals 1/3 nm c bar squared. So that is the RMS speed squared, remember? And we also know that PV equals nRT. So we could say, therefore, that T is proportional to c bar squared. So there's that. Therefore, c bar proportional to root T. Okay. So what I would suggest, just looking at these numbers here, when we've doubled the temperature, we clearly haven't doubled the RMS, but to it, have we increased the RMS by root 2 is what I ask myself, and my suspicion is yes. Here we clearly haven't tripled Vs, but have we increased it by root 3? My suspicion is yes, we have. So we just want to test that, determine the relationship, showing your reasoning. So we'll test, is Vs proportional to the square root of T? And in order to do that, we just try these numbers to see if we get a constant ratio. Would be the easy way to do that. I was about to use a K, but I think when you're dealing with gases and such, using a lowercase k is possibly a little bit iffy. So what should I use as my constant? I'm going to go with X. So 100, oh, whoops, that's not the V. So this type of test is pretty common. It's a pretty common thing in these types of exams. It's also 20.36. Where you've got to propose a test to check the relationship between two numbers. And in general, this is the way that you want to approach that. You want to kind of suggest a proportionality, insert a constant of proportionality, and determine that constant for the data that you've been given. And if indeed you get the same answer each time, then it is a constant and therefore your relationship is valid. That's what we're trying to achieve here. Oh my goodness, if I could use my calculator, it would be easier. 20.38. So in this example, x is constant, therefore our relationship is valid. So Vs is proportional to root t, and therefore Vs is proportional to C bar. Hopefully that, I mean, I maybe didn't explain my rationale there enough, but we could see from our data, we could see from the data itself that this Vs is not proportional to temperature. And we're told that this simple mathematical relationship exists. So worth kind of thinking about as a first step, what is the relationship between CRMS and temperature? Okay.